Let us see how we can calculate activation energy by using Arrhenius equation. Arrhenius equation is K is equal to A into e to the power minus EA divided by RT. Write this as equation 1. K is rate constant, A is Arrhenius constant or pre-exponential factor, EA is activation energy, R is gas constant, T is temperature. Here we will take natural log on both sides of the equation. I can write ln K is equal to ln A minus EA divided by RT. Let me write this as equation 2. Now, this equation is of the form y is equal to mx plus c, which is a straight line. When we plot a graph of ln K versus 1 by t, we will get a straight line. Here m, that is the slope, that will be equal to minus EA by R, and the intercept C is ln A. For this graph, intercept is ln A and slope is minus EA divided by R. So from the slope, we can calculate energy of activation, and from intercept, we can calculate the value of A. So from this Arrhenius equation, we can tell that increase in temperature or decrease in activation energy will result in increase in the rate of the reaction. And there will be an exponential increase in the rate constant. At temperature T1, I can write this equation 2 as ln K1. K1 is rate constant at temperature T1, which is equal to ln A minus EA divided by R T1. And at temperature T2, ln K2 is equal to ln A minus EA divided by R T2. Let me write these equations as 3 and 4. So here K1 and K2 are rate constants at temperature T1 and T2 respectively. Now if I subtract equation 3 from equation 4, I can write ln K2 minus ln K1 is equal to ln A minus EA divided by RT2 minus of ln A minus EA divided by RT1. This is equal to ln A minus EA divided by RT2 minus ln A plus EA divided by RT1. So ln A and ln A gets cancelled. We have ln K2 is minus ln K1 is equal to minus EA divided by RT2 plus EA divided by RT. On the right hand side, I can take out EA divided by R as a common term. We are left with 1 by T1 minus 1 by T2. And on the left hand side, I can write this using laws of exponents as ln K2 divided by K1. So this is equal to EA divided by R into 1 by T1 minus 1 by T2. Or I can write this as ln K2 divided by K1 is equal to EA divided by R, and taking LCM, here we have T1 into T2, and numerator will become T2 minus T1. So this is the other way of how we can represent the same expression. Converting this natural logarithm to the base 10, I can write log K2 divided by K1, which is equal to EA divided by 2.303 R into T2 minus T1 divided by T1 into T2. It's if we rearrange this expression, I can write EA is equal to 2.303 R T1 into T2 divided by T2 minus T1 into log of K2 divided by K1. So it's using this expression you can calculate activation energy for a reaction when you know rate constants at two different temperatures.